Hello everyone, welcome to Unit 2 of AP Physics C, Electricity and Magnetism. This unit is all about capacitors, capacitance, and also dielectrics, which we'll get into in a minute. And so this one's a relatively short video because it's a relatively short unit, and we'll just be going over a few of the most important topics in this, and then I think 6 practice problems after that. And yeah, that's going to be it for this unit. The next unit would be a pretty big one. It's circuits and things like that, so buckle in for that. But for now, it's just capacitance. It's one of the shortest units in E&M. So what is a capacitor? A capacitor is just, it's going to be two conductors that are separated by an insulator. So the most common example is a parallel plate, where you got one conductor on each side, and then you usually get air or some other insulating material in the middle. And so when you quote unquote charge the capacitor, that just means that the same magnitude of charges on both conductors, but they're opposite signs. So one of them is net positive, one of them is net negative. And so overall, the capacitor still has a net zero charge, but we still say it's charged because each side of the capacitor has its own charge. And so if you have something like positive Q here and negative Q here, we say the charge of the capacitor is Q, even though it's technically zero. But yeah. And we also need to talk about the potential difference between them. I think a little, you covered parallel plates a little bit in the previous unit, and you did talk about like electric field between them, which is always going to be straight. And we know that electric field is always in the direction a positive test charge would go. And so it would be going away from the positive side towards the negative side. So that's the electric field. Just quick recap of last unit. And the potential difference between them is V, usually written as VAB for the potential difference between the plates A and B. And the formula for this is capacitance, the quantity that describes how much a capacitor can hold is capacitance. It's kind of like the breaking point of a capacitor. So that's going to be equal to the charge over the voltage between them. And so you can kind of think of it as if you have some amount of charge, the potential difference between them is a certain value so that the capacitance is constant. That's always going to be a constant. It doesn't change. It's unique for each capacitor, and we'll get into that in a second. But that usually is constant. And you can add more charge if, it's like a different current going through the capacitor, and that would change the potential difference between them. And there's usually this breaking point for the potential difference. Like if it's past a certain value, the capacitor just breaks down. But we don't really go into that much. It's just this ratio would always be constant. Now, the unit for capacitance is farad after the scientists, and is just equal to 1 coulomb over a volt, because those are the units of charge and potential difference. And how would you calculate the capacitance? So this is one way, but what if you're not given the charge and potential difference? Because those do change, right? Instead, I told you that for each capacitor, there's a unique capacitance, and the formula for that is it's equal to epsilon naught times the area of each plate, so of a singular plate, divided by the distance between them, the separation gap. And so the reason why is because of the fact that you can calculate the formula for the voltage or potential difference of a plate, like an infinitely long sheet basically, using stuff from last unit. And if you plug in that formula and you simplify, you can cancel off a Q and you get this as your answer. Because there's something to do with surface charge density. I believe it's surface charge density over distance, if I remember correctly. And surface charge density is Q over A. And so that changes stuff. Let's see. So that's the general formula for capacitance. You would probably use that multiple times throughout this unit. But moving on to an example of capacitors in circuits. So circuits is next unit, but we kind of briefly touch on capacitors in circuits in this unit itself. We don't really talk about current and all that, but we do talk about voltage through a circuit. And so there's two different types of circuits, series and parallel. We'll talk about parallel first, and that's basically where there's different branches that current can go through. So it can either go through this branch or this branch. Series is that there's these two elements, and it goes through both of them at the same time. So if you have capacitors in parallel, the symbol for capacitor, by the way, is these two lines like this. So if you have them in parallel, how would you calculate the equivalent capacitance? So like the total capacitance of this entire system. In parallel, voltage is the same. So the potential difference across this branch is the same as across this branch. The reason why is because think of it like, so this electric potential, think of it like gravitational potential, which we didn't really talk about, but it's just gravitational potential energy divided by mass. And so if you have like a hill, and you roll a ball down this way and you roll a ball down this way, it's going to be the same change in gravitational potential energy. You can roll it down as many ways as you want, but as long as they're like different paths from each other and you cannot take both paths at the same time, that's the same, that's like an analogy to this, because it's going through different paths and it cannot take the same path at the same time, or it cannot take different paths at the same time. And so it's going to be the same exact scenario, which means the change in potential energy would be the same. And if we apply that here intuitively, you see that the voltage would be the same across different branches for a parallel circuit. That's not like a full proof, but just to, I guess, help you remember or to interpret it intuitively, it's a good thought. So we know that voltage is the same. What about charge, though? Well, unlike voltage, which is just potential energy, that doesn't depend on the path taken, charge can either go in one of two ways. It cannot go both ways. And so whatever charge goes here, all the other charge must have gone through this path. It just diverges. And so the charge, you actually have to add them to get the total charge. So if you have a certain amount of charge Q here, this one is Q1, this one's Q2, and Q1 plus Q2 equals Q. For voltages, if it was a certain voltage over there, it's V1 equals V2 equals voltage, because they're the same as the original potential difference as well. And so you can use this fact to find out that in parallel, the equivalent capacitance is equal to just the sum of all the capacitors. You can just plug these into the formula and you would get that. So if you do something similar with series is the complete opposite, because it's just one path. And so the potential energy, or in this case, the potential, would not be the same for both of those capacitors. Instead, it would be like the charge. It would add up to be the total. This is like if you have a roller coaster or something, and you drop a ball down this part, and then you drop a ball down this part, they're not going to be the same potential energy. Let's say this one was much bigger. But instead, the sum of those two would be equal to the total. And that's the same scenario happening here, but with electric potential energy instead. And so here, V1 plus V2 equals the total voltage. For charge, though, when a certain amount of charge comes onto one side of the capacitor, let's say it's electrons, right? Because we know that electrons are the ones moving, but we also, like, thanks to Ben Franklin, we say that conventional current is protons moving, even though we know that that's not the case. You can do either. Why not? Let's do conventional current and say there's a positive charge on this side. And that means there would have to be an equivalent negative charge on the other side of the capacitor, which means a bunch of air quotes, massive air quotes here. Protons are moving from this side of this capacitor to the next side, or the front side of the next capacitor. If you did it the other way, you would say the electrons are moving there. And so this would become a positive Q and a negative Q as well. It would be the same value of Q. That's important because it's the same magnitude of charge that is moving from one capacitor to another when you initially get this charge on this first capacitor. Because it started off neutral. This side started off neutral and then became minus Q. And so that plus Q had to go somewhere. It's just leaving this capacitor and going to the next capacitor. And so that means the charge across different capacitors in series is going to be equal to the total charge. And so what does that mean? Well, it's not as intuitive here, but that just means that the equivalent capacitance is equal to, 1 over the equivalent capacitance. The reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of all of the capacitances in the series. And so those are the two formulas you should probably know. This is kind of how you derive them, because if you plug this back into the equation, you would get these out. Okay, so that was a bit about capacitors in series and parallel. Then energy. So capacitors store energy, and the formula for that is U is equal to 1/2 CV squared, where C is capacitance, V is potential difference, and that's also equal to 1/2 Q times V. Because again, C is equal to Q over V, so Q over V times V squared is just QV. So those are the two formulas. How would you get that? Well, you know that potential energy is equal to the negative integral of the force times, it's just equal to the negative work. And so work is equal to integral of force, and so you would just use that. I don't think you would be asked to derive it. This is on the formula sheet. So that's, there you go over there. And there's also something, I'm not sure if you learned about it, but there's the the energy density. So it's just energy per unit volume, and sorry, that's not a mu, that's a lowercase u. And so it has its own formula, which you can derive, but you're probably not going to be asked to do it. It's 1/2 times epsilon naught, which is actually a big player in this unit. Epsilon naught is pretty important, times E squared, where E is the electric field through the parallel plate capacitor, this electric field that I was talking about. So yeah, that's those are some more formulas you should know. And then we get to the last topic in this unit, which is dielectrics. So dielectrics are basically insulating materials that can fill the space between the two conductors in a capacitor. So if you have like these parallel plates and you put in like some plastic or some paper or something there, it has its own dielectric constant kappa, or sometimes just K. But that's just like this value that's always going to be greater than 1. That describes the permittivity of that material. So the kappa of a vacuum would be 1, because it's just vacuum. This, by the way, epsilon naught is vacuum permittivity. That's the vacuum permittivity constant. And so to get the permittivity of any other material, you just use the vacuum permittivity and then multiply by kappa, because kappa is basically the ratio of permittivity through a certain material to a vacuum. So if you have the permittivity of some value here, you divide that by the permittivity through a vacuum, and you get kappa for that material. For air, it's about 1.005, I think, which is negligible. It's very close to 1, and so we just treat air as a vacuum in this case. That's why throughout this entire thing, we're not multiplying epsilon naught by anything, because even though it's air, it's close enough to 1 that it works. And so how does kappa get involved? Well, the actual capacitance across a capacitor is equal to kappa times the capacitance if there was no dielectric. And so that's just equal to kappa times epsilon naught times area divided by d. So it's this equation, but multiplied by kappa because there's a dielectric. You can also replace kappa epsilon naught with just epsilon for that substance or material. But it probably gets confusing. Kappa epsilon naught is a bit easier because epsilon naught, it's going to be the same no matter what. And almost every time you see an epsilon naught now, you can just add a kappa in front of it if there's a dielectric. For example, in this formula right here, the new potential, the new energy density is going to be 1/2 kappa times epsilon naught E squared. Like I said, epsilon naught's a pretty big player here. And where else can we add a kappa? Well, if you remember back to last unit, there was a pretty big place where epsilon naught was, and that was Gauss's law. And so that's basically the last thing we talk about in this unit, Gauss's law, but with dielectrics. And so that's basically just saying the integral of E dA is, the surface integral is equal to the Q enclosed divided by, instead of epsilon naught, it's kappa epsilon naught. And so you can multiply both sides by kappa epsilon naught to just get Q on one side, but it doesn't really matter. This is the new form of Gauss's law when you have a dielectric. That's basically it for this unit. There's some other stuff, like small details that you should probably know that I'll be talking about later when I'm going through the problems, but that's basically it. There's just one last thing I want to mention. It's not always going to be parallel plate capacitors. It might be like a spherical capacitor or a cylindrical capacitor, where you got like a cylinder on the outside, a cylinder on the inside, and both of them are conductors with an insulating material between them. That's technically a capacitor. Now, we're not going to find the formulas for that. The formula for capacitance of a non-parallel plate capacitor is not this. This is not, this is only for parallel plates. this is for everything, but this is only for parallel plates because, like I said, we had to plug in V is equal to that surface charge density over D into that equation to get this formula. But you can derive it using this. Like I said, we plugged in V equals the formula for a parallel plate capacitor into this to get that. And so if you know the potential across any other shape, like a sphere or a cylinder, then you can plug it in here and you'll get a new formula for the capacitance. But you're probably not going to do that. There's one problem we're going to cover today that does involve that. So that's why I just want to preface that. But it's not going to be that prevalent in the test. So yeah, that's it on capacitors. Moving on to the practice problems. So this first one here is parallel plates. So we love parallel plate capacitors. The magnitude of the charge is 240.0 pico coulombs. So pico is nice because it's it's not used that much outside of like E&M because pico is very, very small. It's 10 to the power of negative 12. And so we're going to deal with a lot of picos in this unit. Pico coulombs, pico farads, all that. You're not going to be dealing with pico volts because a volt is not that big of a unit of charge. But coulombs and farads are. Sorry, not charge, voltage. Okay, so you have that. And then it says the potential difference between them is 42 volts. Like I said, you're not going to deal with like picovolts. That looks like 420. Okay. If the area of each plate is 6.80 centimeters, what is the separation between the plates? So now we know, sorry, this is not capacitance, this is charge. I mixed up the unit. Okay, so we know capacitance is equal to Q over V, and that's also equal to epsilon naught, so there's no dielectric here. So it's equal to epsilon naught 8 over D. And we know this, we know that, we know that, we know that, we just don't know D, so we solve for it. You can move the epsilon naught A to the other side and get D is equal to epsilon naught A times V over Q. Plugging in what we know epsilon naught is 8.85 times 10 to the power of negative 12. We know A is equal to, it says 6.8 centimeters, which you would convert to meters squared. So that's 6.8 times 10 to the power of negative 4 meters squared for A. For V is 42, we know, and Q is 240 times 10 to the negative 12, or 2.4 times 10 to the negative 10. And so you're going to get a total separation distance of 1.05 times 10 to the power of negative 3 meters, which you can write as 1.05 millimeters. And so that's a pretty small distance, but for a capacitor it makes sense, because capacitors are pretty tiny. For part B, if the separation between them is double the value calculated in part A, what is potential difference required for the capacitor to store a charge magnitude of 240 picocoulombs on each plate? So it's basically this exact same equation, but we're resolving it for V instead of D. So divide both sides by V, divide by D, and then reciprocal. So V is equal to QD over epsilon naught A. And so you plug in what we know. Q is 240 again, picocoulomb. So 240 times 10 to the negative 12. D is twice this, so that becomes 2.1 millimeters, or 2.1 times 10 to the power of negative 3 meters. And that is, epsilon naught is 8.85 times 10 to the negative 12 again. And A is still 6.8 centimeters squared, so it's 6.8 times 10 to the negative 4 meters squared. And so you plug all that in, you get a voltage of 84.0 volts. And you find out that's exactly twice what it was before, so it's 42. And that just tells us that, like, when you double the distance, you're going to have the capacitance, and when you have the capacitance, you're going to double the voltage. So it's kind of like this relationship. You didn't really need to calculate all this if you thought of that, but in a free response, you probably should show all your work. So when you double distance, that becomes half capacitance, and since voltage is in the denominator, it's also inversely proportional to capacitance, so you basically double the voltage. And so those are answers for the first question. Not that difficult, very common problem you'll see in capacitors. For this next problem, it's a circuit, or not a circuit, it's like capacitors in series and parallel. So we know the potential difference is 25 volts. what is the equivalent capacitance of the system between A and B? So we can use our formulas here. We have these three in series, and so first let's calculate that. So we know in series it's 1 over C equivalent is equal to 1 over C1 plus 1 over C2, in this case plus 1 over C3 because there's three of them. 1 over C1, so C1 it says is 18.0 nano, so nano is times 10 to the negative 9, but we don't really need to worry about that now, because if we keep the units the same, we can ignore them and have our answer in nanofarads for this as well. So this is just 18.0, this is 30.0, and this is 10.0. You're going to need a calculator for this, 1 over 18 plus 1 over 30 plus 1 over 10, and then you do 1 over that entire answer. You're going to get a C equivalent of 5.29 nanofarads. Remember the nano. So you can replace all that with a capacitor. So let's redraw the circuit. So we replace all those three capacitors in the middle with just one that's 5.29 nanofarads. This was 7.5 nanofarads and 6.5. So now it's in parallel, and we know in parallel you add them up. So it's C1 plus C2 plus C3, and so you just do 7.5 plus 5.29 plus 6.5, and you're going to get, if you use sig figs, 19.3 nanofarads. And so that's our final answer for part A. Part B, how much charge is stored in the system? So we know C equals Q over V. V is 25 volts. C is this, 19.3. And so you just do 19.3 times 25, and you get a total charge of 482 nanocoulombs. Remember the units, because nanofarads, just volts, come out to be nanocoulombs. Part C, how much charge does the 6.5 nanofarad capacitor store? So this one's a little bit interesting. Remember I told you not just, you don't need to only know these, you also need to know how voltage and charge behave in series and parallel. So we can kind of backtrack here. In these parallel, voltage is the same. And so it would be 25 volts for all three of these branches. And so in this branch, it's 25 volts. And we know the capacitance, so we can find the charge from that. C equals Q over V, so Q equals CV. So you just do 6.5 times 25 to get the charge, and that's equal to 162, again, nanocoulombs. So it's a little bit tricky there, but you want to kind of backtrack. Instead of just calculating the equivalent capacitance, sometimes you want to bring it back to the individual components. And finally, what is the potential difference across a 7.5 nanofarad capacitor? Well, we kind of already calculated that. It's 25 volts across all of these, and so it would be 25 volts for that one as well. So V 7.5 is equal to 25 volts. And that's our answer. All right. Moving on to the third question. This is about energy in capacitors. So you got 8.38 joules of energy. Separation is 2.3 millimeters if the separation is decreased to 1.15. So it's basically halved. What is the energy stored? A, if the capacitor is disconnected, and B, if it remains connected. So I'll get to that in a second. That is one of the small little details I wanted to mention during the problems, because it's important to know, but it's not really strictly part of this unit. It's just like a fact you should know. So what is the formula for the energy stored in capacitor? It's equal to 1/2 CV squared, which is also equal to 1/2 QV. And another form, I didn't really mention this because you're probably never going to use it, but it's also 1/2 Q squared over C. Yeah, just getting rid of the V. In this case, you might want to use that, but it's still hard to tell. So first, if separation distance is halved while it's disconnected. So when you disconnect capacitor from the voltage source or whatever, now that means charge can no longer flow to the capacitor, but the voltage is free to change in any way you want because it's not connected to a voltage source. It can be anything you want, except unless it goes past the maximum possible, but we don't care about that really. And so the charge is constant, but voltage varies. When it remains connected, Well, it's connected to a voltage source. It cannot deviate from that voltage, but the charge can move because it's connected with wires, and so the charges can move through the wires away from the capacitor or towards the capacitor, depending on what the voltage says. And so if the capacitor remains connected, that means potential difference is constant, charge varies. If it's disconnected, charge is constant, potential difference varies. Important to know here. So in part A, charge is kept fixed because it's constant, but separation distance is halved. So we know C is equal to epsilon naught area over distance. If you halve the distance, you're multiplying the capacitance by 2. So C is now twice what it was before. Now we do use this formula because we don't because voltage can vary, so we don't want that in the formula. But Q stays constant, so this entire thing will stay constant. We know capacitance is now doubled because of this, and so the potential energy should be halved because C is in the denominator. And so your new potential energy would be half of 8.38, which is 4.19 joules. Part B, if it's still connected, that means potential difference is constant, charge varies, and so we want to use this formula because we don't want charge at all in our equation. Here, voltage is the same, so that's constant. All we care about is C. How does C change? Well, again, C is doubled because distance is still halved. And so this time, potential energy doubles because it's directly proportional to C instead of inversely proportional. And so it's 8.3 times 2, which is 16.76 joules, or 16.8, based on sig figs. So that's your answer. All right. Moving on, we got 3 problems left. These ones, this one is pretty interesting. This is the one I was telling you about where you have to kind of derive the formula for a capacitance. This is for a spherical conducting shells. So here you got 2 spheres. One of them is 12.5 centimeters. The other one is 14.8 centimeters. And potential difference is 120 volts. And we want the energy density. Well, the formula for energy density is equal to 1/2 epsilon naught times E squared. And in this case, we don't really care about capacitance of the spheres. We care about the electric field between the spheres. And so we still need to find voltage in this case because we know that voltage is equal to the integral of electric field with respect to R. And so the electric field is equal to the derivative of voltage with respect to R, because integrals and derivatives are opposite from each other, or they undo each other. So what does that tell us? That tells us that that we need to find the voltage. So how do you find the voltage in a spherical capacitor? So we know from like the shell theorem that whenever you're inside a sphere, the charge doesn't make you feel any electric field. It's only when you're outside the sphere. And so when we're between the spheres, which is where the electric field is, the outer sphere doesn't matter. It can basically not exist at all. It's just the inner sphere that matters. And so the formula is the voltage is equal to just the general formula for electric potential, because we can also treat spheres as just points at their center when we're outside them. And so it becomes Q over 4 pi epsilon naught R. And in this case, we've got a potential difference between two places. And so on the outer space, it's going to be RB. In the inner sphere, it's going to be RA. And we know RA and RB, but for now, let's just not use that, because that's going to, we can kind of generalize this formula first and then plug in what we want. So you can factor out a Q over 4 pi epsilon naught, and you get 1 over RB minus 1 over RA, which you can actually simplify if you want by just, multiplying by RA and RB. It's just like normal subtraction of two fractions, right? You find a common denominator, and so it becomes RB minus RA. So this is from A to B, by the way. So that's why it's B minus A, because this, by the way, should be A minus B over here. I didn't specify that it was A to B, and so it's A minus B, and then they swap places when you actually subtract the fractions. So voltage from A to B is this. So it is positive. And so what can we do from that? Well, we know that electric field is equal to Q over 4 pi epsilon naught R squared, because that's the formula for electric field. And we also know that this is equal to voltage from A to B. And so if you want just Q over 4 pi epsilon naught, which is the same thing we have in this expression, we can just move this to the other side. So that means Q over 4 pi epsilon naught is equal to VAB times, this is the reciprocal of that, because we're moving it to the other side. And now you just plug it into this equation for electric field. We get electric field is equal to VAB, RARB over RB minus RA times V over R squared, because that is still outside. All we substituted for was Q over 4 pi epsilon naught. So this is VAB, by the way. And now we can plug in what we know. So we know that RA and RB, so RA is equal to 12.5 centimeters, RB equals 14.8 centimeters. And in this case, I don't think we need to, well, actually, yeah, no, we do have to convert to meters, because it's not just straight centimeters over centimeter. It's centimeter squared over centimeter, which we don't want. And so we have to convert to meters. It's just divide by 100. And then we know this is 120, because it says that in the problem. And R is what's changing. Initially, it's 12.6, then it's 14.7. So we just plug it in, and we get E is equal to, so RA and RB we plug in, V we plug in. The general R we're not going to plug in yet, so we can actually get a formula for it. You get 96.5 times 1 over R squared, or just 96.5 over R squared, because all of these were constants that we had. Now we just plug it in for R equals 12.6 centimeters, or 0.126 meters, and R equals 14.7, or 0.147 meters, and we get E is equal to, you just plug that into R, and you're going to get 6.08 times 10 to the power of 3 volts per meter, or also newtons per coulomb. And then you plug it into this formula. We know epsilon naught is 8.85 times 10 to the power of negative 12. And we know that E is now 6.08 times 10 to the power of 3. And so we get U, which is energy density, is equal to 1.64 times 10 to the power of negative 4. And we know it's joules per meters cubed, because energy density is just energy per volume. For the other one, we plug in for R for 0.147 meters, we get an electric field of 8.85 times 10 to the power of negative 5. And so U is equal to, U is equal to that. I skipped a step. E is 4.47 times 10 to the power of 3. U is equal to 8.85 times 10 to the power of negative 5 joules per meters cubed. And then part C, for a parallel plate capacitor, the energy density is uniform in the region, except near the edges of the plates. Is that also true for spherical capacitor? No, because we just found out that the energy densities are different for different places in the sphere. What this question is saying is parallel plates, it's a constant electric field. Whether you're here or here doesn't matter. Here, it does matter. Where if you're here and here, you're going to experience different energy densities. And so that's what it's asking. So your answer for that is no. All right, just 2 problems left. This next one is about dielectrics. And there is something I didn't mention about dielectrics, which I'll get to in this question. So you got the capacitor without any dielectric has a capacitance of 5 picofarads when there's air. Yeah, so air is just vacuum in this case. We treat it as vacuum. And distance is 1.5 millimeters. What's the maximum magnitude of charge Q that can be placed on each plate if the electric field in the region cannot exceed 3 times 10 to the power 4 volts per meter? This is kind of what I was talking about earlier, where there's this maximum potential difference you can have, and In this case, we're given the maximum electric field, which you can use to calculate the maximum potential difference. So this is without a dielectric first. We know voltage is equal to the integral of E with respect to R, where R is like the distance basically. And in this case, since it's a constant electric field, we basically just went over that. It's a constant electric field between parallel plate capacitors. It's just equal to E times the distance between them. So V equals ED is a formula you should know for parallel plate capacitors or anywhere where electric field is constant. If it's not constant with respect to position, then you use this. In this case, E is equal to 3.00 times 10 to the power 4, and D is 1.5 millimeters, which is 1.5 times 10 to the power of negative 3. So you're going to get a V of 4.5 times 10 to the power of 1, which is just 45 volts. So that's the maximum voltage you can have, but you want the maximum charge, and so you just use C equals Q over V, or Q equals CV. And in this case, C is 5 picofarads times 45 volts, is Q is equal to 225 picocoulombs as your answer. Part B, you do have a dielectric, and the dielectric constant is K equals 2.7. And so it does mention this, electric field cannot exceed this, it's the same number again. And so how would you solve this? Well, you would just plug in for this new capacitance. So this voltage stays the same because the electric field maximum is not changing. And so voltage stays the same, it's just the capacitance is changing because it's a dielectric in between. And we know that C is equal to kappa times C naught, which is one of the formulas I told you before. It's just equal to kappa times epsilon naught A over D. But we don't care about that in this case because we don't know area. It's just kappa times C naught. And kappa is 2.7 times C naught of 5. And so you're going to get 13.5 picofarads. So C is equal to 13.5 picofarads. So now you just plug that in here. For C, instead of 5, you plug in 13.5 times V of 45. So you're going to get a Q of 608 approximately picocoulombs as your answer. And so what's interesting here is, I didn't mention this, but dielectrics also have something called the dielectric, like the breaking point of the dielectric. So dielectric strength is this kappa value, but you also got dielectric breakdown. So it's kind of like what I was talking about, where if you have a certain potential difference or a certain electric field, your capacitor breaks down. You also got dielectric strength in this case, which is what causes, like, that is the maximum possible electric field before you can, before it breaks down. So in this case, it happens to be the same as with air, but it doesn't always have to be. So yeah, that was that problem. Last problem here. Parallel plate capacitor area of this separated by that of Teflon. So it expects us to know the dielectric constant of Teflon, which I don't think you're supposed to know, but I'm just going to tell you it's 2.1. If it was on the test, it would give you 2.1 as the dielectric constant of Teflon. So calculate the charge on the plates when they are charged to a potential difference of 12. So we know C equals Q over V. We know V, and we're trying to find Q, so we just need to find C. Well, we know C is equal to kappa epsilon naught times A over D. We know epsilon naught is 8.85 times 10 to the power of negative 12. We know kappa is 2.1. We know area is 0.0225 meters squared. And we know D is 1 millimeter, which is 1 times 10 to the power of negative 3 meters. So you plug all that in. We do basically everything here. You're going to get 418 picofarads, which is just 4.18 times 10 to the power of negative 10 farads. And to find the charge, you plug that in here, and you get Q equals CV. V is, it says 12 volts times 418 picofarads is Q equals 5,020 picocoulombs, which you can write in scientific notation. I just like writing picocoulombs. You could also write it as 5.02 nanocoulombs. It doesn't really matter, but, you know, it's up to you. B, uses Gauss' law. So this is where I was telling you the last topic we learned in this unit is Gauss' law, but with dielectrics. And so you use Gauss' law to calculate the electric field inside the Teflon. So you got Gauss' law, which is the integral of E with respect to A is equal to Q enclosed over kappa times epsilon naught in this case, because we got dielectrics. So electric field is constant because, you know, it's parallel plate capacitors. So it becomes just E times A is equal to that. And so you get Q, you're solving for electric field. So you divide by A, you get E equals Q over kappa epsilon naught times area. Q, is this. We just calculated 5,020 picocoulombs divided by kappa of 2.1, epsilon naught of 8.85 times 10 to the power of negative 12, and A is 0.0225. So you solve for E, you're going to get 1.2 times 10 to the power of 4, and the unit's newtons per coulomb. So that's with the Teflon in there. Part C is voltage source is disconnected and Teflon is removed. So when voltage source is disconnected, we covered this before, it means that the voltage can change how much ever it wants, but charge is the same. So this is going to be the same charge, but voltage will be different. And let's see. Teflon is removed. So we don't have that kappa anymore. And so we have to find the new capacitance, which is just without this kappa. So you're basically dividing this by 2.1. You're going to get a capacitance of 199 picofarads. Oops, should not box that. Yeah, 199 picofarads, because 418 divided by 2.1 is 199. And from that, we know this exact formula, but without the kappa. So here, electric field is equal to Q over epsilon naught area. And Q is still 5,020 picocoulombs. Epsilon naught is 8.85 times 10 to the negative 12. Area is 0.0225. And so you can solve for it. So we didn't really need to find capacitance, but it's good to solve for that. You're going to get 2.52 times 10 to the power 4 newtons per coulomb. You'll see that once you do that, it's going to be a stronger electric field, because dielectrics kind of dilute the electric field. It is because during through a vacuum, it's going to be the strongest possible it can be. When you got like plastic or some other insulating material, it's going to weaken the electric field. All right. And that's it. That was our last question. And so we're done with this video. It was shorter than usual, but still a pretty long video. And so, yeah, that's it for capacitors and capacitance. And I'll see you in the next one. So good luck for this test and the AP exam. And I'll see you with circuits, which personally is my favorite unit in E&M. So I'll see you then.